Okay, week 3, we're going to talk about pulse width modulation, which is what we were introduced to last week in week 2. Basically, we use pulse width modulation or duty cycle in order to modulate or proportionally control how fast or how slow an implement or a cylinder moves. We'll talk about power flow today, and we'll also get into reading schematics and why we have to have them. Okay, pulse width modulation. We talked briefly last week that when we run electric motors, solenoids, and lights, we often need to throttle them up or modulate how dim or bright or how fast or how slow they move. They simply will not work for us only in an on-off mode. This is accomplished with pulse width modulation. So we don't just want something to go on or off. We want to modulate how fast or how slow something moves. Textbook terminology, PWM. To put it simply, for direct current electronics, we are modulating the on-off time of the voltage to control the output of an electrical device. For example, 90% on time would be a bright LED or a solenoid with armature or cylinder almost fully extended. On the other hand, 10% on time would be a dim LED or an armature or a cylinder that's only partially extended. PWM is generally controlled by a transistor. The transistor can supply either power or ground. This is what the symbol looks like when we get into schematics. When we talk about duty cycle, the fraction of one period in which a signal or system is activated. Duty cycle is commonly expressed as a percentage or ratio. A period is the time it takes for a signal to complete an off and on cycle. Here's an example of what you would see if we use one of those old school oscilloscope screens. If we could run whatever it is that we're trying to do through the oscilloscope, this is what you would actually see. So for 20% duty cycle, you would have 20% on time. If you compare 20% to the 50%, we're basically on for an equal amount of off time. Then obviously 80% is the exact opposite of our 20%. So our 80% on time versus our 20% off time is the exact opposite to our 20% duty cycle. This is an example of the transistor and how our control signal comes in and how it goes out to where we're going to use it. When we talk about power flow, we talked a little bit about it last week. At this point, we should all be under the understanding or the assumption that power flows from the battery. Positive or power to ground. Along the way, it passes through components in a simple circuit, for example, a switch, maybe a relay, fuse, a resistor. When we talk about conventional theory, this theory assumes that power leaves the positive terminal of the battery, completes the circuit, and returns to the negative terminal of the battery or of the power source. This is the method we have used while working in this course, and you probably used it in rig maintenance one as well. And we talked about the right-hand rule last week, power in, and our magnetism lines about the ends of our fingers applies to conventional flow. Here's a demonstration, or here's an example of what they consider conventional flow. From the positive, through the light bulb, back to ground. When we talk about series circuits, a series circuit is a circuit where the resistors, or light bulbs, in this case maybe, are linked in a chain, one after the other. Only one path exists for the current, and the current is the same for the whole circuit across the board. Voltage is the sum of all of the voltage drops at each resistor or at each light bulb in this case. Here's an example of when we talk about a series circuit. Leaves power, or the positive, goes through each light back to negative. If we want to calculate the voltage drops, we add each of them together, and that gives us our voltage drop for the circuit. Very similar to the old school Christmas lights. When one light bulb in the strand of 200 goes out, the whole freaking thing don't work. So you got to find that one light bulb that doesn't work to fix the Christmas lights. We talked a little bit about parallel circuits. In this case, there's more than one path for the current to flow, unlike a series circuit where it's one big chain. Voltage is the same at each leg of the circuit. The voltage doesn't change from one to the next. It's equal at all three light bulbs or resistors. Adding current total at each leg gives you the total current of the whole circuit. This is the most widely used for us over series, as it uses less wiring. We don't need as much wiring when we do stuff in parallel as opposed to series. And here's an example of basically how a parallel circuit works. One wire comes out of our positive, branches off basically in 3 spots, and then comes back to our negative, just like in our series circuits. It's an example of a series parallel circuit that we find on a schematic. Now that we're going to get into schematics, here's basically what you're going to see for the symbol for a battery. Basically, this is where we're always going to start when we're looking at a schematic or trying to troubleshoot. First thing we want to do is find the battery, and where our negatives and our positive goes from the battery. Okay, schematics, what are they? Basically, we need a map of the electrical system on a truck or a piece of equipment before we even begin to diagnose why something is not working. It's a map from start, from battery positive to the finish, which is the battery ground or the frame. Without a schematic, it can be really unclear of what wiring components are in the system. So in general, when we look at a wiring schematic, it's basically going to tell us or show us a map or a road map, however you want to visualize it, of all the different circuits on that particular machine. So it's going to give us a lot of information on one picture. So we do have to be able to visually break it down. When you look at something like this, it would be very hard to pick out where exactly our problem is if we can't break it down from circuit to circuit, which is where our schematic is going to come. FYI, when I use the term circuit, I'm referring to a certain part of the electrical system. For example, dashboard dimmer switch circuit on a service truck electrical system. So basically each component is going to have its own circuit. If we look at a horn, it'll have its own circuit within the schematic that makes the horn function. Lights will have its own circuit. The radio will have its own circuit. Basically each electrical component or operation is going to have its own circuit within the entire schematic of that machine. When you work in a busy wiring circuit, like the one on the previous slide, it helps to have a neatly labeled map of the different circuits to chase a problem. These maps will use wiring numbers, plug numbers, orientation components, as well as other information. So this is where we get all the information for our schematic. It's going to give us our symbols, it'll give us harness numbers, wire gauges, colors, all the information that we're going to need to narrow in on a problem that we're trying to troubleshoot. A battery ground is always hooked to the frame of the vehicle. That way, any circuit can be completed by finishing its connection to the frame. So ground wire or the ground cable from the battery will always go to the frame of the machine. For example, if this cable goes to the battery negative or the negative terminal on the starter, it's also going to go and ground to frame. That way, any of the circuits that we have in the cab or on the machine, if they need to run the ground to the frame, to save on wiring, to run it all the way back, obviously, to the battery, they can find multiple ground points on the frame to save running multiple different strands of wire for ground. Battery positive must always be insulated to prevent shorts. As soon as we can touch the positive to ground, or if something can ground out to the positive cable, automatically create a short, which means popping a fuse or a breaker. So the positive cable always has to be insulated to prevent shorts. It usually starts from the battery and goes to the starter, and then from the starter to different points. So if it's going to go to say a cab relay or into the cab, it's going to leave the starter and go from there up to the fuse panel or to a cab relay and then a fuse panel, but it traditionally leaves from the starter. One thing to remember, the schematic will show the wiring and the components, but may not be exactly or the exact physical layout of how it all lays in the vehicle or the equipment. So it's going to show you a picture of everything that's on the machine electrically. It's just not going to show you exactly where it's placed or how the harnesses run along the frame or in the cab. Some examples of schematic symbols. So each schematic traditionally has a diagram like this, and it's going to show you all the normal symbols that we use for switches, diodes, fusible links, or fuses. And you're going to find that most manufacturers will follow the same icons or symbols, whether it's a John Deere or a Cat or a Vermeer or an Ingersoll Rand. All of those manufacturers, they might use different components to accomplish different tasks, but they're going to use the same symbol on a schematic to identify what it is. Here's an example of a horn circuit. Again, there's going to be multiple circuits on a schematic. If we're only working on the horn, we need to try and narrow it down from the great big map just to the small circuit that we need to figure out why the horn doesn't work. For this example, it's very straightforward. We basically come off the positive on the battery. Traditionally, we would have some kind of a fuse here. It wouldn't just go right to the relay. We'd have some kind of a fuse. But here it shows that we're powering pin 86, which we know is the control side of our coil. It's also powering pin 30, so this could possibly be a higher amperage than what we're going to send to 86. 87 is going to go to the physical horn, and then the horn is grounded to the battery or to the frame. If we look, we have power at pin 86 on our coil in the relay. Pin 85 is going to be our ground from the relay up to the horn push button. So when you push on the horn or press the horn button, it's going to complete the ground, which is going to obviously, as soon as we complete the ground, it's going to pull our power over and put power from pin 30 to 87, and it's going to make the horn work. If the horn didn't work, we would obviously start here and kind of work our way through the circuit, which we'll get into in a few weeks when we start to talk about troubleshooting. Here's an example of a headlight circuit. It gives you a little bit more in-depth information. Here it tells us what our relays, each of our relays are doing. So we have 2 relays, and we have our left and right side, high beam and low beam. We're starting here at the battery. So this is our last one. You can see our connection to ground, our frame. We're going to go through a fuse. We're coming down here to our relays. And we basically have power sitting at pin 30 on both, ready to go, depending on which switch we use. As soon as we use, say for example, our low beam, we hit the low beam switch, we provide power to the control side of the coil. The magnet in the coil pulls the terminal down to our low beam wires, and we basically supply power to both left and right low beam. When we turn the low beams off or use our high beams and switch the rocker switch, we supply power to the coil side on our high beam relay, and then it sends power to the high beam. Here's an example of what we're looking at over here. So 87A on both relays, they're telling us high power output, right? So it's probably going to be, say a 30 amp. Say we're going to send 30 amps to our lights. 87A, high power output, normally closed contact, so you can see there's no wire attached to 87A. It's just sitting there doing nothing. 87 is our high output, normally open contact, so this contact stays normally open, right? There's no contact here until we put control power to the coil, which is 86, I believe. Coil relay feed, or our trigger wire. Another example here, we have two relays. We have a battery power fusible, so we have a fusible link here. It's 30 amps, so it's supplying constant power to pin 30 on both relays, which tells me that there's basically 30 amps or power at the ready on pin 30. We're going to use our switch, 12 volts, right through a fuse, and this is going to be basically an arm switch or a safety switch, say for example in the cab. So we're gonna put the arm rest down, or the safety switch. We're gonna close that. It's gonna supply power to pin 86 on both. So there we have power at the coil. We're ready to make each relay function as soon as we close the ground side of the relays. So pin 85 on each. We're basically controlling what happens from the ground side this time as opposed to the positive side. So when we use our throttle micro switch, so say we throttle it up and we close our fuel safety switch, it completes the ground to the relay, which allows power to flow to our fuel on solenoid or off solenoid and to our nitric solenoid. So this example, we're controlling the negative or the ground side of the relay, as opposed to our headlights. We were controlling the power side of the control, or the control power on that solenoid. Coil, sorry, for the relay. Lastly, when using a schematic, you can skip to the known bad section if you want, but I generally move from one side to the other, power to the ground side, checking both resistance and voltage. So it doesn't matter how you go through the schematic. Everybody kind of seems to have their own